Good morning, ladies and gentlemen. Nice to see you. So, what we will do today is that will be third lecture of our course. Time goes fast. So I checked whether we have finished the second lecture. Just to recall, it was about quantum interference. And eventually, we will talk more about quantum interference, and one of the strange conclusions would be that classical effect, classical Ohm's law, in fact, emerges from quantum interference. But that will be only a small cherry on the tart, and we will have more challenging program, which we need to have, because we learn physics not only like separate blocks, 1, 2, 3, like in military academy. I always like to compare the present structure of bachelor education at this department to military academy. But well, it has to be done in such a way at certain stage, because several generations before you, people gladly took 10 years to finish bachelor studies, so it had to be organized. But okay, an impact is that you have less connections between different subjects. You learn to study by blocks. Right, that's not what we want in general from a physicist. For a physicist, all these blocks have to come to one big united picture, right? That's why we made quite some attention to an attempt to reconcile scattering approach to transport and usual approach which you study perhaps yet at school, that the total resistance of two resistances in series is the sum of the resistances. All right, that would be main topic, and we will cover it at large, and that will include many things about quantum transport, but also I will tell quite a bit about usual ways to describe, say, conductance in solids, which would be more like classical transport. Good. With that, we will understand the value of finite element approach, both to classical and quantum phenomena. Right? And with this, I will try to give you a taste of finite element approach to quantum circuits, to quantum series, which includes scattering, transmission coefficients, stuff like this, that we will study in the end of this lecture. And lecture number 4 will be concrete examples of this quantum circuit series. Okay, so let me perhaps repeat the outline shortly. At the moment, we kind of have learned 2 blocks. One is what you get in 2 previous lectures, quantum transport as scattering of electron waves. Another block, which you have learned perhaps at school or when it was first year at the university. It's about electric circuits, which you describe in terms of resistances, capacitances, whatever, where Ohm's law is essential, circuit elements are essential. Usual approach to electricity propagation. Right, and we're gonna make bridges between these two opposite sides. Simple bridge, and in that case, I will derive all this stuff from quantum mechanics. And the golden bridge, and in this case, I would see how these approaches, which are pretty useful, pretty powerful, we will discuss why, how these approaches could be used to understand quantum mechanical systems. Good, so challenging problem, and let me start with a simple but perhaps rather philosophical example. Perhaps I made it a little bit too philosophical, but anyway, it should not confuse you. Okay, I will talk about double junction in series. And let me remind you that we have learned quite a lot about this in the second lecture. So there are two tunnel barriers and phase shift between them, which affects interference of the waves propagating through the system. So the total transmission coefficient would depend on this phase factor. You could not just derive it from transmission coefficients of two barriers which you put in series. All right. But I don't want to repeat this whole calculation, which we have done. I just try to get a simple estimation, all right? Not to calculate much, just try to get simple estimation of this transmission. How would I say, what would I say, right? I would estimate the amplitude of propagation through two barriers, T1, T2. Well, there is some phase shift, but whatever, I assume it's of the order of 1, so it doesn't matter much. Fine. Then in order to get conductance, I need to square it, right? And express it through conductances of the elements. What I get that the total conductance is a product of two conductances. By dimension, I should make a dimension conductors, right? So I would divide it by conductance quantum for proper dimensionality. Well, that's kind of a little bit naive, but rather solid estimation. However, if we treat it from classical side, the estimation is quite different, right? So in this case, we just have two resistances corresponding to the junctions. We know that the total resistance is a sum of two resistances. Now I need to convert resistances to conductances that we remember. So I come with this formula. And it's kind of not entirely inconsistent, right? So this factor and this factor appear to be the same, but denominator is apparently wrong, right? Also, if we scale both conductances with a factor of 2, Ohm's law would tell us that the total conductance will also scale with a factor of 2. But yeah, that gives a factor of 4 apparent difficulty. So one could contemplate quite a bit about this controversy. One can see it as a paradox. Well, fortunately, it's not much to think about because we know the total solution, the full solution of this problem, right? That we, let's see, that we did last time. So in fact, it is necessary in this case to perform a thorough analysis, and one should not restrict to a single trajectory, which we took for estimations. One has to sum up over all trajectories with any number of bounces. Fine. So in this case, we have transmission coefficient, which is a product of transmission coefficients, but it is divided by something which is quite complex. It contains phase factor, I mentioned, extra, remember, A and B, and is always important in this context. Right, and that is the fact is that this denominator can become very close to 0 at certain values of chi, right? And this small interval of chi appears to be important because the transmission in there is very large. That is the plot. So I just plotted it for small t's, small transmission coefficients versus energy or phase factor, that's more or less the same. And I understand the following. The minimum transmission, which is typical here, so in most parts of this interval, I see this minimum transmission. Minimum transmission is indeed proportional to t squared. However, there are peaks at certain values, around certain values of the phase. And peaks are tremendously large, of the order of 1. So the conclusion is that at average, the transmission coefficient is not t squared, is much bigger. It is of the order of t. This is already in accordance with Ohm's law. And indeed, if we just average transmission coefficient over chi, as it is shown in second formula, then we get something which, well, is very much resembling Ohm's law, right? If we neglect the last term in the denominator, it would be just Ohm's law. Fine, right? That we roughly understood, but the point is that we, for any practical device, we do not perform this averaging over chi. So, how to deal with this? So let us make next step, and let us understand that if there are many channels in our conductors and the energy dependence of these peaks is different for different channels, then the result will be kind of self-averaged. Here that I have demonstrated with this plot, and if you look attentively, it consists of many colored curves. Oh, somehow in this display they don't see very much colored. Anyway, believe me that these sine curves, they're colored, and they have the same pattern, very large peak, one, and very low bottom. Right? The periods in energy of all these curves differ a bit, so that thick black curve is the result of averaging. And already for 6 channels, you see, well, it doesn't go too far. It is somewhere about 0.3. So there is some self-averaging. If you increase number of channels, then we expect it to be more flat in this plot. Right, good. So that is assumed here. I assume that the channels are independent. Well, it's convenient assumption, but let us investigate whether it's really true. So that is a formula, and if the channels are independent, we have this Ohm's law within each channel, right? So first term, sum over channels, and we have this nice combination of transmission coefficients. Well, it's not quite done. Second term is what actual Ohm's law would tell us. Oh, what's wrong there? What one has to take into account? Something which rather difficult to set into formulas, at least the formulas which we can evaluate, but it's rather easy to tell in words. Or at least I will make an attempt now. The channels are not independent in the space between the junctions. They are mixed, or one can say that the channels defined in the first barrier do not mix the channels in the second barrier. Okay? So the space between the barriers cannot be characterized just by a single phase shift or diagonal phase shifts for each channel. Rather, it is a unitary matrix. Why unitary matrices are related to phase shifts? That one, let's see, do I have it on next transparency? Not really, so one needs to say it in words. Perhaps you know it or you can recall it quickly. What one can say about eigenvalues of a unitary matrix? What can you say about?
The norm is 1?
Yes, so the eigenvalues are complex numbers with modulo 1. One can say that the decanoization of scattering matrix would lead to a set of eigenphases. a set of eigenvalues, and all of them are 1. Right, sir. In fact, it means that it's one introduces here plenty of phase shifts, simultaneously mixing all the channels. Good. I wouldn't be able to do Revit simply, but believe me, that restores Ohm's law in the limit of big number of channels. So it's just a second. So we have just a kind of more or less practical criteria, experimental criteria. Ohm's law is satisfied for conductors with a big number of channels. Then it will be a result of self-averaging. Yes, your question, please.
So are you saying that the channels are interacting with each other?
They do not interact, just they are just mixed, right? So let us imagine some ideal waveguide, for instance. Then we have learned what's there. We have distinct transport modes which go through this waveguide. Let's have some distortion in this waveguide. For instance, scattering on impurity or something like that. Then if you send a wave in one channel, it will be partially transmitted or reflected in another channel because of this imperfection in impurity. So in other words, one can say one cannot connect these conductances without certain imperfections. One cannot connect these conductors keeping the same channels in both conductors. All right, that's why one needs this unitary mixer. Fine, more questions? It's kind of important thing to understand. So, I mean, if I were a student, I would prefer this transition would be simpler. It is not. So one has to think of quantum interference. One has to think about many channels, self-averaging of phase vectors. But well, whatever, that's a basis of quantum transport, in fact. Fine. Let me go further. Let me talk more about the importance of phase shifts, and simultaneously let me talk about disorder and randomness in nanostructures, which we can make now. They say technology develops fast. They always tell this about technology. As a matter of fact, it does develop, but right, it's the scale is rather, time scale is rather long. When I was in your age, and nanostructures just came into practice, I expected they will become like 100 times better in, say, 10 years. All right, that was about 30, 40 years ago. Now they're perhaps 2 times better. Technology does develop, but it doesn't do it as fast as we like. And at present day of technology, and I guess the present day would last for about a century, we cannot control phase shifts in nanostructures we made. For simple nanostructures, we can make it and tune a couple of parameters. but it is to understand that the number of these phase shifts between scales as L² of the conducting channels, right? So already with few channels like 10, the number of parameters you're gonna control becomes unpractical. Right. So if we make formally identical samples, we got different phase shifts, and we need to deal with that. We need to deal with randomness, which we encounter in nanostructures. Randomness also means some ignorance, right? Also, it's not plausible to fully characterize all peculiarities of a nanostructure, and you would never actually completely understand the random object from a practical point of view. Right, it has to be functional. So this is a table, it has a functional table, and it has many scratches and things like that, but yeah, it's not, doesn't belong to this function. One should not worry about this. One has to be ignorant about this. So perhaps we don't have to know all these phase shifts to work with quantum nanostructures. Right, what is the similarity? What is the similarity between different learning blocks in your physics course? Oh, what is that? Something terrible. It is important concept of physics says when it becomes completely messy, it also becomes ultimately simple, and statistical physics gives plenty of examples about this. Say, in order to air in this room contains zillions of molecules, and each molecule has a velocity and position, and that's too much information for us. We only care about a couple of parameters: temperature, oxygen content, pressure. Right, that's because we describe the air not as a collection of molecules, but just object of statistical mechanics. Right, so it is we learned that averaging over phase shifts simply restore classical concepts of transport, basically suppression interference. We would formally have to average over the samples. But if there are many channels in the sample, we don't have to, because there's self-averaging for the case of big number of channels. That restores Ohm's law, which is pretty classical concept, which does not use waves. But the point to recognize that there are conditions at which Ohm's law is restored, but electrons in your nanostructure are still waves, still quantum mechanical waves. In elastic processes, which I shortly mentioned in the first lecture, do not spoil quantum character of the waves, do not bring any decoherence, which we study later. So it remains quantum mechanical, but it looks like classical. All right, any questions? Perhaps I went too philosophical, trying to talk about general things, so please give me some feedback. Not really, you kind of like it, you can follow. Good. In several lectures, we also talked what would be quantum effects for many channel systems, what would be deviations, weak localization, corrections, universal conductance, fluctuations. We will come to this points. So, yeah, it takes time to appear. So with this, let me switch the gears and let me tell you something which you could have learned in solid state physics, but now physics becomes more complex, and teachers usually don't have time to explain you that. In my time, it was still a part of solid state physics course, at least in some form. And that is about usual approach to electron transport in solids. What was the problem about 100 years ago and how people solved it? In 20s, I understood that electrons in solids, in metals, are eventually quantum particles. They understood that these particles are waves, and if there are no impurities in this metal, they could deal with the problem easily, right? You recall it from your solid state physics course. There are Bloch waves, eigenfunctions, the spectrum of electrons in solids, everything is fine. But there is an important measurable quantity in solids which cannot be estimated, derived in this Bloch wave picture, namely conductance, electric conductance of the solids. Why is it so? Because in a perfect solid, conductance is infinite, right? So electrons could go through solid without any resistance, which is not realistic. There are always impurities. So at high temperature, they could also scatter on vibrations of the lattice. They could also hit each other, these electrons. But at sufficient little temperatures, the impurities is the main source of resistance, the main source of finite conductance. Okay, but if you put these impurities into your solid, you complicate the picture of the waves immediately and tremendously. That's what I wanted to sketch on this slide. So there is one of many electron waves in the crystal, right? It is shown as a regular sequence of wavelengths. But when this regular sequence comes to the impurities, you know what happens? Each object like this becomes a source of the waves, right? So there are radial waves which come from each impurity center. And already for 3 impurities, the wave pattern is very complex. But well, for realistic sample, we have zillions and zillions of impurities, and it is really completely impossible to consider it as a wave pattern. Right, that was a problem people encountered 100 years ago. Fortunately, people were also smart, but at that time they were not cavemen and women. They were just practical people, and they understood simple thing. We, instead of thinking of waves, one can return to the concept of electron as a particles, as a ball, which goes through crystal and is scattered at the impurities from time to time. Good. And they put these ideas into a formalism, which I will shortly outline. I'd like to finish before the break, but I also don't want to give you a feeling that I missed something or cheat on something. Sir, please break me if you wish. Good. The balls, the particles. Next point is that we don't want to follow each particle. It would be also kind of overkill, the resilience of electrons in the crystal. Instead, we would like to think of particles which are near some point x in coordinate space and near some point p in the space of momentum. And we just count how many particles are there in a small interval of coordinate and in a small interval of momentum in momentum space. That gives us idea of distribution of particles. This distribution is a valid intuitive classical concept. This filling factor which depends on x and momentum, but also it can be derived quantum mechanically. What I have to do, I have to invoke density matrix since it depends on x and momentum. I would want to make a partial transformation, Wigner transformation, Fourier transformation with respect to difference of coordinates in this density matrix. Then I have a function which is in quantum mechanics is called Wigner function of it's a function not of two x's as density matrix. It is a function of x and momentum. Right. And that can be associated with classical distribution fxp. Right. Then there are two ways to proceed further. One could, in principle, start with quantum mechanical definition like this and try to solve quantum mechanical equations. It's a kind of nice exercise, but beauty of the approach is that you don't have to do this. From that point on, one can proceed with classical physics. What helps is the fact that a number of particles are conserved, right? Number of particles in a small cube. Now my challenge is to picture a six-dimensional cube. I didn't do it lately. Fine, let me picture a two-dimensional cube. So suppose x and momentum are just in one dimensions. All right, then the number of particles in this interval, small squared in this space, should be always the same. All right, that might seem boring, but let us understand that this squared eventually moves in time within this two-dimensional space. Why is it so? That's what I put here in yellow. The coordinates of particles change in time depending on momentum, and also momenta change in time depending on force, which is gradient of potential, which depends on x. So this squared is moving in time. And if we, and this conservation is very simple in moving frame and rather trivial. But if you just rewrite it in lab frame, it will become more interesting. And this is normally called Boltzmann equation, which is not quite what Boltzmann did, but yeah, it's based on his approach. Fine, that's good, but we are still in ideal situation. We still describe ideal waves, although we describe them as particles. So we have to.
Yeah.
Yes.
So why is the number or the density of particles the same everywhere in the phase space?
No, it is not the same. At the moment, this, it is field vector, let me confess this. This field vector is a function of both coordinates and momentum. And we don't think yet about any equilibration or anything. We just consider a big collection of particles. So it's not a constant, it's really a function of both x and y. But what is important is that its evolution is given by this equation. Fine. We need to describe these impurities, and that can be done since we are talking about distribution, since we are talking about probabilities, with a simple statistical approach, which is in a little bit different context, is called master equations. Right. Let us concentrate on, let us look at electrons which have different values of momenta, pi and pi prime, p and p prime, sorry. And let us consider different processes which can change the probability to B and Z momenta. First process is scattering. So you start from the state P prime, right? It comes with, sorry, I have to also to show it to some participants. It comes with a number of electrons at P prime, and then there is some scattering probability, which depends on impurity concentration, on the properties, but there is only a scattering probability to go from pi prime to pi. Okay. There is also another process. There is is that when you are in the state pi and you scatter to all possible states, this probability comes with minus sign. Here it is. Yeah. Have a closer look at these two terms. Well, for instance, if F doesn't depend on pi, these two terms just cancel each other, it would be the balance of scattering processes. But well, any master question looks a bit like bookkeeping. You have incoming terms, some income, and you have spending terms, some outgoing terms. So that comes to the state pi from all other states, this plus term, probability is increased in this given state, and the scattering from state pi to all other states. So there is a spend, this term is minus sign. Good, so we can combine that conservation approach and scattering. Right, and that's kind of usual microscopic theory underlying the modern calculations of transport of quantum electrons in bulk solids under classical circumstances. That's right. Let's have a break, like 8 minutes break till 9:40. Yeah, 9:40. Fine. So let me repeat what do we have now. We have made several steps. So we introduce the distribution of electrons, filling factor, number of field states in a point of 6-dimensional space, coordinate space and momentum space. We understood that without impurities, one doesn't have to write complex quantum equations for that, because one can derive everything from conservation of particles. That presumes that particles move continuously. They don't jump in coordinate space. They don't jump in momentum space, right? The evolution is given by these equations. There are many French names. That's called Liouville approach to particle dynamics. Yes?
Well, the one part I don't understand is the total number of particles would be the integral over phase space of F.
Yeah.
So conservation of particles would mean that the time derivative of this integral should be 0.
Yes.
And that's weaker than just saying the derivative of F should be 0.
Perhaps a little bit misunderstanding. Let me draw this picture again. To derive this equation, for each point x and p, we consider a small squared. We count how many particles are there in this squared. Then we switch time. Time goes on. This squared changes this position and perhaps size. That we understand? Following these equations. Fine.
Okay, yeah.
My statement is that after the motion, it contains the same 5 particles. So we apply this conservation to each element. If we are in coordinate system which moves with each squared, that is quite trivial statement. But instead of this we just look here, we have many squares passing, and we have to take this into account that the squares are moving. This is done with this Liouville transformation of coordinates. So from full-time derivative, we have partial derivative in time, and also derivatives of coordinates in time.
So is the size of the square constant?
It doesn't matter. These squares are infinitely small. Right? You might go to logical problems if these squares are smaller than the number of particles. But, well, as far as distributions are concerned, you can, it doesn't matter. You can assume that they are infinitesimally small. Like you cannot have 1/1000th of a particle in your squared, but you can have probability 1/1000th to be a particle in the square.
And if the volume was not infinitesimally small, then two different particles inside the volume could move apart.
Yeah, that could be. There's some problems with quantum chaos in this approach, right? When two close trajectories would go apart after some time. But it still does not affect Liouville equation.
Okay.
It makes it impossible to trace its solutions, for instance, with a computer, but the equation is there. Yes?
And also, if these particles are electrons, we are not modeling the repulsion between those electrons in this model.
At the moment, there's no interaction, so there are independent particles. One could kind of make some, with some assumptions, one could, and we will actually do so, one can say, well, for instance, this force also is contributed by all other electrons in the system, right? And express this through density of electrons. That would give rise to an equation which is nonlinear in field vector. One could do so. But at the moment, it's simpler to talk about this. There's enough complication with the Liouville equation already. Right, and that was the Liouville equation. And then we add scattering processes. Why does it have to be changed? Why the situation has changed? In the process of scattering, electron changes momentum drastically. It jumps to another state of momentum, and that cannot be captured by continuous Liouville equation. Good, that can be captured with this bookkeeping tool, with master equation. When we introduce probabilities to go from state A to state B and back from B to A, and write the balance of the probabilities. To characterize these probabilities is a separate task. For instance, we could formulate quantum mechanical scattering problem for each impurity. Yeah, for instance, it's the ion of calcium in underlying iron, and formulate the problem of scattering of Bloch wave in iron on this individual calcium atom. The result of this calculation would be probability, which will depend on two values: incoming momentum, outgoing momentum, and energy should conserve. But it's a separate calculation which one can do apart, concentrating on a single impurity, while this equation tells you about all impurities in your sample.
So normally when we talk about like everyday material, we think about diffusing conductors, right?
Yeah.
So we have to think about inelastic scattering as well.
That I don't know, that depends. But let's talk about diffusion. Right. We are not done yet because there are still several simplifications we can make after all. Yeah, and what is that? Next assumption which you can make is that distribution of electrons in momentum space is almost isotropic. How does it come about? Let me have p space, let me have a surface of the same energy, right? And electrons, when scattered, just go to random points of this equipotential energy, of this energy equipotential, right? And several scatterings is already enough for such isotropization. That means that if the space scale is sufficiently long, if the space scale is such that electrons cannot traverse this scale without several scatterings, their distribution function must be almost isotropic, right? Sure, it's a concept of mean free path, certain lengths at which electrons will scatter on impurities, and at space scales larger than this mean free path, the distribution can be regarded as isotropic. Good. What we can do with this, we can have the concept of diffusion. What I write here is in fact diffusion equation. I just prefer to write it in a little bit unusual manner. Good. So now f is a function of coordinate only. The reason for that its dependence on momentum is redundant. There's some remaining dependence on momentum, and that provides asymmetry in momentum distribution, and that leads to a current. A little bit more electrons on this side as compared to this side. It means that there is a total current of particles in this direction. Fine. And this current contains two terms. Second term is a gradient of particle concentration. That's natural, right? If you have more particles in some regions, they would go to the left. There will be gradient, so there will be current proportional to the gradient. There is also effect of force, and that involves derivative of distribution in energy. Good. So this is what people call drift diffusion equation. Awful sound. When I visited my dentist like last time. Fine. Okay, let's disregard it, as we disregard many things in this formulation. Sir, it's a drift diffusion equation. Diffusion, this coefficient d, terms proportional to the gradient of concentration, and drift, where is the drift? Drift is this term proportional to force. That's also a little bit a Jude approach, which you mentioned. There is a velocity of electrons, which is proportional to force, which acts on these electrons. Good. The next step is integrating this guy over energy. We have not yet done it. Here, F is still function of energy in each point. If scattering is elastic, it doesn't matter. If scattering is inelastic, as you suggested, it could change. One would have to introduce some inelastic scattering, Boltzmann-like terms, a balance of different energies. All right, but let me integrate it over energy. I try to get it simpler and as fast as possible. Good. If we integrate this part over energies, what we get is just density of particles, right? If we integrate left side, we got the current. And this is continuity equation. I wonder if you have it in some different context, perhaps in hydrodynamics or whatever in mechanics. It different comes in play. It's a continuity equation, a conservation of particles in coordinate space. Let me rewrite it. Derivative of density with respect to time is a divergence of current. Fine. And what is the current? It contains two terms. One is proportional to force, which is electric field. And if we talk about electric current, the coefficient of proportionality, the sigma, is called conductivity, precisely. Right, and that one could eventually disregard if one talks about good metals, because in good metals, density of electrons is zero, precisely, okay. Right, so in ideal metal, you cannot just have electrons localized there. There could be some surface charges on this metal, but not in the bulk. So in the bulk, this term can be cancelled. Fine, what we got? We have a system of differential equations to describe transport in meteor with a known conductance. Yeah. That's an example. For instance, we have this gray thing made of three conductors, and we want to understand what is the conductive properties. We want to understand what the resistance of the thing. All right, it has three legs, it has three terminals, so we would have to compute what we called, remember, lecture number 2, conductance matrix. Right. How do we do this? Okay, we have computers, right? So we take these differential equations, we discretize them properly, right? There are programs, subroutines for that. We put it into computer, push the button, it will give us the answer. Catch 22. In order to make a computer, in order to design a computer, one has to understand the conductance of such things, the conductance of small elements of your computer without using the computer. Okay? And that great step has been made by here. Wonder if you know the guy. This family name in this transparency, but it's not very explicit. So who can tell who is in the picture? Kirchhoff. Right, Gustav Kirchhoff was a German professor which lived in the middle of 19th century, and he understood basically how to get from equations like this to finite element approach to the circuits, right? And it was not very academic, and he eventually, to take you something not about physics but real life, he had hard time to get professor position. It took him like 30 years, and finally he could work in Dresden. But it was not the time where practical things were appreciated by academic community. What he gave to us is a simple idea that things like this can be reduced to finite elements over to very small discretization. If you would solve equation for this element, we would have to discretize it anyhow, even in the computer. Simplest discretization would be to represent it as a single node somewhere here, and three conductances corresponding to the legs. All right, now we can solve the circuit. How we do so? We fix voltages here, here, here. We don't know the voltage here yet. How do we compute that? We make balance, we use Kirchhoff Rule. What is the balance? It's very physically intuitive. The sum of the currents in the node must be 0. But the currents are functions of voltages. So from this, From this we can solve for this voltage and finally find currents in each leg. Good, so we find 3 currents as a function of 3 voltages. That was what kind of Kirchhoff has derived, and since the middle of 19th century, all engineers applied this. It kind of opened up electricity for engineers and finally led us to all these technological developments of modern times, including computers. Good, let me let me go on, and now I will try to do the following. Kirchhoff equations are based on a simple concept of conservation of the balance. And let me give quickly a couple of examples where this balance can help us to understand simple situations of quantum transport. All right. First example, let me get back to this double junction system. And let me have many channels, so this kind of Ohm's law, everything is averaged. And let me try to do it with a balance of currents. I assume elastic scattering, non-elastic scattering. In this case, I can balance currents at each energy. And what would be current at each energy? All right, it will be given by Landauer formulas. Remember Landauer formula? It's a difference of filling factors on both sides of the junction. Right, for junction 1, it is left and filling factor in the node. For junction 2, it's right and filling factor in the node. Fine, the sum of 2 currents must be 0, Kirchhoff's law, at each energy. From this we can solve for filling factor at each energy. And what is here, what is plotted here is the answer. Filling factor, remember, this is the axis for filling factor. It is a step here on the left, step here on the right, and in the middle we have, how many steps do we have in the middle? How many steps do we have in filling factor in the middle? One and two. Start the recording. Good. Double junction. Energy conservation. The junction is too short for inelastic processes to take place. So we have conservation of current at each energy. We can compute filling factor, which depends on energy. It has 2 steps. Full current from this derivation just recovers Ohm's law. Fine, that's what we expected. But we also have this funny filling factor as an output of the calculation. Let me do something more interesting. Suppose we have inelastic scattering. which comes from electron-electron interaction. What does it mean? They collide, they exchange energy, and as a result of this, they assume some equilibrium distribution function. What would be this equilibrium distribution function? It would be a kind of Fermi distribution. Fermi distribution is characterized by two numbers, by chemical potential and effective temperature. Fine. You still have to understand what are these temperatures and effective potential. Two unknowns. But these two unknowns, we make two equations using two conservation laws. One conservation law is a conservation of charge. Right? That's the first line here. You see now I integrate over energy because I don't have conservation at each energy separately, only total electric current. Right? What would be another conservation law? It's conservation of energy. Electron collide, exchange energy with each other. At the moment, there's no energy flow outside of the nanostructure. Right, that is gives me another equation. Fine, which I can solve. If I solve it for chemical potential, that would be, well, somewhere in between chemical potentials of these metals, right? If conductances are the same, it would be right in the middle. As to the temperature, okay, one can argue already from scaling arguments, from dimension arguments, that it will be also order of voltage applied. So even if temperature is 0 in the bulk, electrons in the nanostructure will be hot. Again, it's for sufficiently long nanostructure so that electrons have time to feel each other, to collide with each other, when traversing the nanostructure. Fine. Third slide is very simple, but it's yet another answer. Current is the same, filling factor is different, right? So now I make the junction, the spacer between two junctions so long that it could give heat outside. If there's a difficulty, I just implement a small fan to make it cool. I make it cool, so then the conservation of energy doesn't apply. I end up with only conservation of charge, which gives me Ohm's law immediately. Here we are. So for all these three examples, the current doesn't change. The filling factor is very different. One can see, for instance, this effect in current noise. Current noise is very different for these three setups. Very good. And I have a little time to talk about quantum mechanical conservation laws. At the moment, we've been dealing with classical conservation laws. Balance, it's all about money, that we kind of learn from childhood, how to deal with money. Money doesn't disappear unless you spend them. That gives us a good understanding of classical conservation laws. Right, now I want to talk about conservation laws in quantum mechanics. And I have some philosophical parts. and practical parts. And I guess I could talk about philosophy today and about practical parts in the next lecture. It will also have better connection to the material of next lecture. First of all, let me talk about conservation of current in quantum mechanics. There is a good criterion to understand whether your quantum mechanical book, your textbook, was good or not, because there are many books in quantum mechanics of different quality. All right, let's skip this joke. Of different quality, and good way to recognize is to check first 20 pages of the book to find this derivation. Since it's in first 20 pages, many students just see it once and forget it immediately. But it is in any good quantum book, and it has to be there because it's very fundamental for justification of quantum mechanics, Schrödinger equation, which is, I guess, owing to Schrödinger himself. Right, so what is that about? Suppose we have a Schrödinger equation and wave function that obeys Schrödinger equation. Next to it, we want to understand what is the current of probability. Fine. And what we can do, we cannot derive completely, but we can try an expression to see whether it can be used as a current probability. Good, that expression contains two wave functions. Every physical value should contain two wave functions, right? And a gradient. Here it is. Right, then there is the derivation at page 19 of Griffith's book, if I'm not mistaken. Right, that one can just compute divergency of this current. Compute divergence of this current with the help of Schrödinger equation. It's manipulation of the gradients, and after that, one obtains that in stationary case, the probability current conserves. Quantum mechanics makes sense. If the probability would rise from nothing, or disappear to nothing, it would be very bad for quantum mechanics. Fine, conservation of current in quantum mechanics. The idea which I want to tell you is that quantum mechanics allows for more conservation laws than classical physics, which has practical convenience. One can use these conservation laws to write balance equations for quantum mechanical situations. Balance equations which are not present in classical description. Right. So what is the trick which I want to demonstrate? Let's take the same Schrödinger equation. Let's take two solutions of this equation. Psi and chi. The energy can be different or the same. And let me just run the same calculation, defining current like this, through psi and chi. The result of this calculation will be zero, at least if the energies of these two solutions are the same. Zero divergence, which that means that we have conserving current. It means that we have conservation of something, and we can make balance out of this conservation. No? I just make it like this. I could take psi conjugated, but yeah, I prefer to do it like this. There are some more physical examples. For instance, one can recall that in wave function, for electrons, we also have spin. What does it mean? Wave function has two components. The spin up, spin down. And we can arrange the current in the same way using these two components. What we will have a matrix current. It will have two indices. Right? And what will it describe? It will describe conservation of spin current, if present. Right, so this one can introduce density matrix in spin indices. Diagonal part of this density matrix would be just electron density. Non-diagonal parts will correspond to densities of spins in three directions. And right, there will be conservation of spin for each projection, for each direction, unless I take into account spin orbiting direction. That's one example. Another example, I have to mention something about magic mirrors before that, which I have skipped before. Right, magic mirror, let me say a couple of words about magic mirrors. Right, that is very common mirror that we see every day. In this case, the wave vectors of incident and reflected light are different. Yeah. This one step of magic's retroreflection is when the direction of reflected light is precisely opposite to incident light. How many times per day do you see such mirror?
50 times.
50, good. So if you think you don't see it, just look at the back side of any bike. There is a small retroreflector over there. But there is a higher degree of magic when it's not only the same direction, the phase of incident and reflected waves are the same. Phase conjugated mirror. Right? That will require a little bit more involved physical situation. You cannot make it on your bike. You can do it in optics using nonlinear effects and laser pumping. Or one can do it with electrons, considering reflection from superconductors. In any case, you need to have two waves. You cannot have phase conjugation with the same type of waves. You can have only, you need to have at least two waves, say red and blue. Fine. So suppose I have the situation and would like to make conservation laws. Okay, here I have conservation laws from magic mirrors. Although it's all magical, we have wave function which has two components. One can form this current, and it conserves provided it's Hamiltonian time reversible, provided there are no magnetic fields in there. Very good. I can tell you more. My time is over. So at the moment, the main issue, main message, is that quantum mechanics can provide you with some extra conservation laws, which are normally absent in classical physics. Good. Thank you for your attention. It's over for today.
It's just a reflector. So if you grab your car at night, shine the light on the traffic light, it lights up.